So we are live. Welcome to the QuantUniversity AI Spring School. As you all know, we have been hosting these sessions for the past many years now, talking about various aspects associated with quantitative finance, how artificial intelligence and data science is influencing the whole world with respect to newer methodologies, integrating alternative data sets, and also some of the various aspects from a business perspective on the fintech side of things. And it's always my immense pleasure to bring in experts from various disciplines who are kind of also in this world of learning new things, but also enhancing their by bringing in different ideas and applying into their disciplines. And as an academic, I kind of, appreciate the rigor and the math, but I also respect and deeply appreciate how quantitative finance professionals are applying these in the real world. And we don't have the benefit of, solid ground truth, wherein we can always go back in time and say, this is what we were looking at, and this is where we are coming from, and basically say that this is going to be something which we can always rely on. We always have to think about like how have things changed, and how do we factor in all the nuances of things which happen in the real world, and basically factor that in and try to model as best as we can. I was just sharing on LinkedIn earlier, back in the day when we used to do Monte Carlo simulations and we had very little data, you had to basically fit whatever you were able to do in a statistical model, starting from the basic, normal distribution, just two parameters, mean and standard deviation, and see what best we could do to replicate these scenarios. But then as we get more and more sophisticated with incorporating various things, you have to factor in all the fat tails and building in all the different distributions. So it's always fascinating to see how to model various kinds of phenomena we observe in the real world through statistical distributions. And Jorg, I've known Jorg for many, many years now, so he is coming back to give this guest lecture, which I really appreciate. I still have his book on my bookshelf on risk, and I always go back to some of the basics, which, as quants, we know the past 20, 25 years, we have seen some downturns, and we have seen model risk evolve. We have seen different kinds of risk aspects evolve. And with artificial intelligence coming up, and with all the new technologies out there, there's this whole revolution on artificial intelligence risk management coming up. And as you know, we have hosted sessions with Agus and Jacob and others talking about the various aspects of artificial intelligence risk. But today I wanted to kind of, get back to the basics on how, as quants, we should be looking at generative AI. And, Jorg has put together a fantastic work on synthetic market data generation, focused primarily on Gaussian methods. And he is going to be talking about how you can think about time series imputation, backfilling, yield curve, and volatility surface simulation, all fascinating topics. I can talk hours and hours and days, and I'm really excited about this presentation. The good news is there is also a very concrete paper which Jorg has posted on SSRN, which I'm going to share on LinkedIn, but also I will share it to the audience who are listening in. For people who don't know Jorg, I mean, most of you who are attending should know Jorg, but just to give a formal introduction. So Jorg Knitz is an experienced quantitative finance professional and a machine learning expert. That's a new thing, Jorg. You have put in a machine learning expert. I always knew as a quantitative finance professional, but we are all evolving in our careers to be machine learning professionals too. He's an assistant professor at the University of Wuppertal and adjunct associate professor, University of Cape Town, lecturing in holding a PhD in stochastic analysis and probability theory, all things near and dear to my heart, stochastic analysis and probability theory. He's a sought-out speaker and has written several journal articles published by leading journals like Quantitative Finance, Journal of Computational Finance, and Risk, and authored 4 books with Wiley and Palgrave Springer. His latest affiliation is with MRIG. You should expand that for me, Jorg. And prior to joining MRIG, Jorg held positions at LSEG, Acadia, Deloitte, Postbank, Deutsche Bank, and as a head of quant. So welcome, Jorg, and please take it away. For protocols, I'm just going to be monitoring the question answers. So the audience, if you are interested in learning something, or if you want to ask a question to Jorg, please post it in the Q&A window, and we will use the last 10 to 15 minutes or so to answer any question answers. And also, before I hand over the stage, I want to mention one new thing we have done, just because we keep getting emails from all of you about slides for the presentations. So what we have done is we have basically put everything on the QuantUniversity AI School. And what you're seeing is a new platform called QSkill Bridge. And I'll tell you at another time on how we are leveraging generative AI to power this platform. But here we are just basically consolidating all the human lectures, if you will, all the lectures with experts have given so far in the last year or so. We'll be incorporating all the past lectures too, but we thought we'll share it in one common platform so that you can just go in there and then you can review all the materials out there. All the slides and the presentations and all those things will be available. I'll be posting a link, and it's free. You can just register and get access to all the prior lectures. And Jorg's lectures will also be updated in the next day or so once we get a chance to get all the presentations and the video together. With that said, Jorg, please take it away. Welcome to the program.
Let me just share my screen. Hope it's visible for everybody. And yeah, thank you very much, Sri, for the nice introduction. And you managed so many positions and stuff. So it's time to recognize how time flies, and that one is getting old, actually. But nevertheless, so still active. And yeah, I'm currently affiliated with Emmerich. It's a small consultancy in Germany, in Frankfurt, actually. And yeah, we're doing some research, some consulting stuff on market risk, credit risk, and machine learning, actually. Yeah, let me start with a quick outline of the talk of today. So I will give a brief introduction, then I will discuss some what I call Gaussian methods, and yeah, you will of course immediately see why. And then I want to use these methods for generative AI applications. So on the way to these applications, I will also mention a little bit the maybe more fancy neural network stuff, but we are not discussing this here. We're just sticking to what I think is something like a powerful but still explainable and simple methods, but we will see. So some examples of the stuff I'm discussing, mainly by showing some pictures, some results, and so forth. And finally, I conclude, give a little summary, and point out some stuff for future research. Okay. So quant finance. So Sri mentioned now everybody has machine learning on the card or wherever, and I think no quant is really complete somehow with not touching actually the machine learning area. But machine learning is a wide field, and what I understand actually on which I label machine learning is also clever statistical methods. So something which we all have used over the last years, and now it's somehow returned. So whenever I attend workshops or talks about machine learning, I think the very basics go back to regression, and I think this is what it is all about, a new fancy way with new ideas, a little bit more power in terms of high performance computing, about new architectures which can handle certain types of problems which weren't available years ago. And of course, nice software frameworks, widespread packages for specific tasks, actually, what one is able to use free of cost. So open source software is also a very a promising field here to look into. A lot of stuff which is available can be directly used. And actually the stuff I'm discussing in the basic setup can be used with just using, so for example, in Python, the scikit-learn package. So what I want to discuss is actually in the generative setting, in the generative AI, say, not application of large language models, but I want to consider generative AI for financial time series, for financial structures. And as I said, I do not want to apply these fancy neural network techniques. So everybody maybe have stumbled across the variational autoencoders, the yield curve generations with the variational autoencoders, this generative adversarial networks, QuantGANs, which are used to generate time series and so forth. Big fancy architectures. And so I thought, is it really the stuff you want to use and you want to apply in this setup? And are there more easy, more accessible techniques? And what I came across actually some time ago, and this will be actually the introduction, is the Gaussian mixture model. And it started with a risk article some years ago, and I used these kind of methods for pricing, hedging, and calibration. And I used these methods, these Gaussian mixture models, to price and calculate hedge sensitivities for very complex models. So it started, of course, with the Black-Scholes stuff. You can get the delta in closed form by just standard formulas. But I was able to extend the methodology for more complex models like the Heston model, the Bates model, the Bergomi model, rough stochastic vol models, and jump models. And just using the generated sample path for that, and use the setup of the Gaussian mixture models, which made me or put me in a position to compute conditional expectations in closed form. And this was quite amazing because these conditional expectations could be used to compute hedge sensitivities, even for Bermudan options in closed form in these models, and also for other applications like exposure calculation, for example. And also in areas like stochastic local volatility models, where you have to compute conditional expectations of variances from simulated values, this could be applied. And this was actually the idea, not starting from a model to generate the path, but taking data which is already available in the market, namely time series data or realizations of curves or implied volatility surfaces, to use them to somehow generate new values. So creating synthetic values by using realized values given in the market. So the first approach was simulating stuff like Bates models, like Heston models, and so on. Use the generated samples and derive certain mathematical formulas, namely conditional expectation, using this method. And in the next step then was use not generated data, but realized data. So without any assumption on the underlying generating mechanism, on the underlying distributions and so forth, just using data as is. Okay, and this is what I'm going to discuss. So first I give you an overview of the Gaussian mixture models, or log normal Gaussian mixture models. So the exponentials of them would be then log normal in this setup. I will show you that any distribution, any continuous distribution, can be approximated with Gaussian mixture models. It's a well-known result, and I will show you some other ideas of using this result. So one, of course, would be if I have any distribution and can fit a Gaussian mixture to it, I could apply every calculation which is available for the Gaussians in this setup for really complex distributions. But another application and an interesting one as well, but this I do in the sequel actually. As I said, the resulting distribution, which is the approximation from a Gaussian mixture model, has several really nice advantages. Namely, you can have the marginals, you have the conditionals, the joint distribution, all in closed form. And this is what we are going to use. We will use stochastic simulation. Whenever we have this Gaussian mixture model, we are able not only to describe a given distribution, but also have a very efficient methodology for simulating these values. And not only from the fitted distribution, but also for the marginals and the conditionals in 1, in 2, in 3, in 100 dimensions. So that's also very, very nice and very interesting. Think about a variational autoencoder or a GAN in more than one dimension. It's complicated, and to get all the training and to get all the architectures right, to do it in several dimensions actually. Okay, this is the conditional conditional and the stochastic simulation, but also a technique, this is what I wanted to mention, is cool in this setup. It's namely that you can morph one Gaussian mixture model in another. And this has to do with this approximation quality of any distribution. And what I will shortly touch here is that with the Gaussian mixture models, it is actually possible to move from the Q, the risk-neutral measure, to the real-world measure P, or to move one volatility surface, one yield curve into the other somehow, and not leaving the distributions of Gaussian mixture models. This is very closely related to optimal transport techniques, which are currently really well applied in quantitative finance, but lack of efficiency because of the complex calculations. But if you can move it all to the Gaussian mixture model space and have everything analytically available, this could be something worth to consider and to apply for these kind of techniques. So in this talk, I will concentrate on backcasting, on market data generation, and so forth. I have in the appendix, which I'm not presenting here, also conditional outlier detection and stuff on exposure and volatility surface transformation in this respect, but this is currently ongoing research. But we tackle only the three topics here. So what is it all about? So Gaussian mixture models is actually very simple. So we take just a natural number k and consider k normally distributed random variables. Could be one, could be d-dimensional random variables. And what I'm going to do here is I'm adding these random variables here, but not in the sense of adding Gaussian random variables, because when I add Gaussian random variables as is, then I would end up in a Gaussian setting. So that's not very fancy, because we want to have more complex distributions. But what one can do is that one introducing a mixing stochastic variable and just choose randomly which kind of distribution you pick. And this is actually equivalent to considering a convex combination of the underlying densities here. So adding, for example, two Gaussian random variables, the blue one here and the orange one here, in the sense of Gaussian random variables, would lead to this Gaussian random variable with this distribution. So it's Gaussian again. But if we fix this convex combination to be for this to both 1/2 weighted and add then the distribution in this vein here, in this sense of adding a convex combination of distributions, we would end up with a dotted line here. And that's clearly not a Gaussian distribution. It has two modes, so it's something different. And this is what Gaussian mixture models is all about. If we would have k components and k Gaussian random variables, we would call a single one distribution here a Gaussian principal component. And this is something I want to stress in the sequel, actually, that I want to use these Gaussian mixtures in the same way as principal components, where principal components have eigenvalues and principal vectors. So the principal components, eigenvectors. In this sense, I using Gaussian mixture models to be the principal components of a certain financial object, of a time series, of a yield curve, and so forth. And the weights could be seen as an equivalent to eigenvectors. So this is what the idea is. This I am skipping. It's just the proof that the Gaussian mixture models are somehow dense in the set of probability measures, and this is that you can approximate any distribution by the Gaussian distribution. And here is what underlies the whole stuff I am presenting. And it's very easy, because once I have a Gaussian mixture model and I have fixed the means and the covariance matrices and the weights, I have the ability to stochastically simulate from this model. And the simulation is very easy. And it is actually implemented in some sense in every financial institution, because it only uses generating normal distributed random variables and uniformly distributed random variables, nothing else. It's not something that you train a variational autoencoder and use this mechanism to generate some stuff from the latent space, and you're not really knowing what's going on. It's actually that simple. It's that I compute a vector, namely the sum of the weights. The first V1 would be the first weight. The second component would be the composition of the first and the second weight, and so forth. Then when I have this vector, I sample a uniform random number between 0 and 1. I choose the index corresponding to this relationship here. So if u is 1/2, I'm choosing the index here, which just adds below 1/2 or equal to 1/2. Take this index and generate a sample from the corresponding normal distribution. So it's very easy. It's just simulating from a uniform, getting an index, and sample from a normal distribution. This is all the stochastic sampling algorithm, and we will see that this simple algorithm is able to create a variety of structures. The parameters, of course. K, the number of Gaussian mixtures, yeah, that's something you have to derive, of course, and also the means and the weights and the covariances, but there are really well-known methods to do that. The method number one is the optimization of the log likelihood function using some version of the well-known expectation maximization algorithm, which is years old and well studied in many situations, used all over the place actually. And the basic variant is available on GitHub in many notebooks. You can explore that in many textbooks. There are a lot of information on this special optimization method there. It can be tuned to sparse settings, to high dimensional settings, and all that stuff. That's a more specific application or a more advanced application. But the basics actually are very well known and very standard. You can, of course, tweak the number of parameters if you're not going for a full covariance matrix, but certain setups where only diagonals are filled, for example, or parametric covariances or kernel type covariances. So that's some idea of reducing the number of parameters in that setting. For other applications, you might want to optimize an objective function. So for example, if we work with volatility surfaces and we want to fit a Gaussian mixture model to an observed implied volatility surface, we want to have an optimization such that we choose the underlying distribution that we are fitting the quoted prices, so the quoted volatilities, that we constrain to have the martingale constraints and everything like that. But that's also quite standard. It's doable via well-known optimization techniques which can handle constraints optimization. Okay, how to get the number? Of course, it's something either trial and error. So in any, say, machine learning, statistical learning method, there are, informed guesses for that. There are methods for determining this number of k, but it's also empirical results that you observe that a certain value of numbers for a certain problem feels just right. So that's some empirical stuff, and it could be somehow supported by other more informed, say, methodologies like silhouette scores, information criteria like Akaiki or Bayes or gradient criteria, whatever. There are some enhancement you can apply, maybe bagging. It's something I applied here, dimensionality reduction, as I said, parametric kernels, kernel covariances that could be done as well. For the method itself, one can work with transformations. So if you want to just work with positive values, you might want to use a log transform so that you apply the Gaussians not directly to the data, but to the transformed data, more involved transformations like Lambert W or Geo-Johnson. So like in other setups, transformations sometimes work really well, sometimes not. But it's also something which could be empirically tested out and applied to a specific problem. Okay, so the Gen AI applications as an initial investigation. So what I want to do, the recipe I'm using, and which you can really use on-site as well, because it's just using the data and it's using scikit-learn functionality here. It's that I'm having some data, time series data, for example, some history of yield curves, history of implied wall surfaces, whatever. There should be just a reasonable amount of data, not not a large amount of data. So I do not want to train tons of parameters of a neural network. So reasonable amount, I mean daily data dating some years back, which is always available for risk management purposes, for example. Many financial institutions just have a daily time series of data. I do not have to have tick data and tons of data for fitting tons of parameter. It's just a reasonable amount of data. The method gives a really high quality fit, even if the data is not that dense as necessary for neural networks. It could be high dimensional data. So for example, a yield curve with 40 points in time, 40 points on the curve could be doable. It could be a 200 dimensional implied volatility surface as well. So high dimensional data is not a problem. I just apply this expectation maximization or this optimization. Of course, if the dimensionality is high, it would take longer for the optimization and fitting all the stuff. That's of course sure, but it can be done and it can be handled. And with the advent of these nice GPUs, TPU stuff, machines, AAD, and whatever it takes to be fast, that could be really doable. And all the examples here I have done on my machine here at home. So it's not a mainframe computer or a very high sophisticated stuff. It's just a PC which you can buy in a store. So not any really high sophisticated machine. Yeah, then the stochastic simulation, as I outlined, is considered. Another trick which I'm often apply is something like, or it's called control variates. So conditional control variates. So when I have some information about a time series, about a curve, I can incorporate it into the setup as well. So that I only maybe fit differences, or I could use some information which is deterministic. So for example, based on some regression results and only the differences are stochastic, then this gives me some further information and is usable, say, in this sense for this methodology. And yeah, there are a variety of applications. And first of all, I show you just some examples. So this is from interest rates, from FX. In this setup, I have only limited data from FX. Usually in FX, you have a lot of data, and equities. But this is just to illustrate the applicability to different assets here. On the left, it's just the histogram of the return data for the different asset classes, and here the transformed data using the Lambert W transform, just to illustrate that you can put them a little bit more into a Gaussian shaped form. And here is what I did. I just took the data, so this return data here, and fitted a Gaussian mixture model to it. And how did I do it? It's simple, because I just used the scikit-learn package. I invoke a Gaussian mixture model, specify the number of components. So you just have to call the corresponding command, which is documented in the scikit-learn documentation. And there you can then use GMM, Gaussian mixture model, and specify the number of mixtures to be k, namely 5 or 10 or 15, whatever you like. And you have to specify the variance that you consider. So it could be the full variance, spherical, diagonal, whatever, but simply invoke this command and specify the number of Gaussian mixture models. And then you put in the data and you just call the fit function. It's like gmm.fit the data, and this scikit-learn application or function invokes this expectation maximization algorithm for you and gives you back the convex combination of the Gaussians. And here is what I did. So I fitted to the data and then generated values, and they look quite similar to the values which I feed it in. So also for the sparse data here, for the FX setup, this is what is generated, and this is what the true data is, and here for the equities. And I tried the same actually with, for example, the QuantUniversity approach, and the data was too sparse for that. Especially this one just gives a point mass. So it wasn't able really to fit this sparse data set, whereas the Gaussian mixtures did a quite good job in this respect. Okay, what I want to use this for, it's not just fitting the data, I want to use it for something. And with one client, we had a project actually where it was requested to use or to fill a certain time series based on the time series universe they had, but if a new company is listed on a stock exchange, for example, or there is not enough data for fulfilling regulatory requirements because the time series is too short, the task then was how to build a time series that has a specific length and taking into account already known information. And this is what I wanted to outline. The idea is actually to take a Gaussian mixture model, fit it to the observed data. So we have, for example, 500 time points where all the data is available. Fit a Gaussian mixture model to this kind of data. Calculate the conditional distribution of the time series we want to generate. Under the condition that all the other time series are known, generate backwards this missing time series using our stochastic simulation algorithm to some point, take the generated path, fit a Gaussian mixture model, do this several times and take the best fitting Gaussian mixture model, and then proceed until we reach the point into the past we are interested in. So generating mock path, I call it. And these mock paths are not just generated at standalone for this time series, but it's a conditional simulation. So the mock paths are generated from a fitted Gaussian mixture model, and then I condition on the realized values, which I already know. It could be the S&P 500. It could be an exchange rate. It could be a liquid stock. It could be a liquid rate, whatever. So these information available, I take, put it into the conditional simulation algorithm, and successively fill back the path I am considering. Yeah, this is my setup. So this idea using Gaussian mixture models. There are others using Ito processes from, for example, Christian Fries considered that in his library FinMatNet, which is available as an open source. And here there are some other resources which use neural network structures in this vein, actually. So how do we consider this backcasting? I took several data sets like Esther, like Sonia, like SOFA, and gilt rates, and I'm currently experimenting with equities, so stocks constituting the Dow Jones index, for example. And let me show you the results. So what I did is I have, as I said, the 2-year rate, 5-year rate, 10-year rate, 20-year rate, and actually the 25-year rate, which I have available. This is what I know, Esther rates, Sonia rates, gilt rates, whatever. And what do I wanted to do? What I wanted to do is to start here and fit a Gaussian mixture model to the rates I have. So all rates, 2-year, 5-year, 10-year, 15, 25, 30 year actually. And, oh, no, 2-year, 5-year, 10-year, 20-year, 25-year, and 30-year. So that's correct. Fit the Gaussian mixture model, generate backwards a path, fit a Gaussian mixture model, do this again, choose the Gaussian mixture model, which gives the best results in terms of the minimum value of the likelihood function, proceed for the next, say, 50 or 100 steps in the past, and so forth. And I have chosen to use the 25 and the 30-year rate here because it's a more challenging problem. It's not an interpolation problem. So you might say if I would use the 2-year, 5-year rate, 10-year, 20-year rate, and would go for the 12-year and the 7-year rate, then it's an interpolation problem. If I know 5-year and 10-year, it should be somewhere in between and produce very good results. But here I'm going for the 25 and 30-year rate because it's an extrapolation problem. And the result is here. So on the one hand side, you see the true time series, which I have available. The green line is using pure Gaussian mixture models, not taking any information, not any time point from the 25 and the 30 year. And it's already very close actually, but not on spot actually. But what I did here is I used this control variate on top in terms of a regression. So I'm using the regressed values to determine the 25 and 30-year rate and add the Gaussian mixture for the differences. And the blue line is what I got. And it's actually fully recovering the path, not feeding in these values into this algorithm. So this is very important. I just use the full values until here. And here I'm just using conditional simulation for the 2-year, 5-year, 10-year, and 20-year rate, and simulate the 25 and the 30-year rate, and going backwards in time using this type of mock path and optimizing the log likelihood of the corresponding Gaussian mixture models. And it gives you nearly the path back. And that's quite impressive, I think, and it's working quite well. And it has another aspect. If we just apply pure regression on these rates, we will see that some characteristics like the autoregression is not preserved very well. Whereas using the Gaussian mixture models, it's very close to the original setup. So if I use the really realized values. And that's quite interesting. So it's really covering the distribution to some sense. here I did it for this conditional sampling, not for just one dimension, but for 2 dimensions, with 4 dimensions being the ones I'm conditioning on. So it's easy to apply it and sample 2-dimensional return distributions using 4 dimensions given as a control, but also 3 dimensions and 3 dimensions. So sampling the 3 dimensions and using 3 dimensions as a control. It's all doable. You could do anything because the conditional distributions are available on closed form. Here it's just an observation that these transformations not always do their job very well. So for example, for already relatively Gaussian distributed data in interest rates, it's not working that well. But for other distributions, like observed in the FX or the equity space, it seems to be giving different and better results. Generating synthetic data for yield curves. Here are SOFR curves, SONIA curves, GILDs, and ESTA curves again. So these are the input data, the training data here. And here is a fit of the Gaussian mixture models and only plotting the mean values of, in this case, just a Gaussian distribution, and the mean values of a Gaussian mixture model with 3 components or 5 components. And here are simulations of these Gaussian mixture models. And it's very interesting to see. So if you increase the number of Gaussian components, you will see a lot more movement or shapes the curve can be constituting, like in short rate modeling, for example, or interest rate modeling. Increasing the number of dimensions of stochastic factors allows for different shapes. But in this case, the means of the corresponding Gaussians, they have an interpretable component. Namely, it's what I term these Gaussian principal components, that you see that the means are something like say a backbone, and the volatility just is varying around this mean. And using this setup, for example, one could see that the SONIA and the SOFR are more related than ESTA is to SONIA or to SOFR, because the Gaussian means, the Gaussian principal components, are much closer to each other for SOFR and SONIA than for the ESTA curve. It's somehow, I found it very interesting to see, and also that the corresponding weights or the analogs to the eigenvalues are closer to that. And once you have the Gaussian mixtures, you can generate these curves. And I compared them to curves generated with a variational autoencoder. And you cannot distinguish between stuff generated with the Gaussian mixtures and the autoencoders. Here, the influence of the components again. So the GMM mean, this is the Gaussian mixture, just the Gaussian distribution. Here, different realizations. Now, 3 components here, and the average component by assigning the weights and summing them up, actually. And here, the realizations of the stochastic simulation. For 7 components, it looks more variable here, and you are able to somehow generate a lot of different curves. Of course, as for any machine learning setup, you have to avoid overfitting, of course. And for this, there are several techniques known to prevent overfitting, but this needs to be really done for each application you do. For the yield curves, I also checked the covariance comparison here for the true values of the curves. So for the ESTA, SONIA, SOFR, GILD curves here, and for a Gaussian mixture model with K components, namely 5 and 7 here. And it's seen here that the generated covariances from the stochastic simulation are very close to the one observed in the data. So the GMM, the fitted GMM, is really resembling the distribution of the realized curves very, very well. And on the other hand side, can produce the main components of the curve as in principal component analysis. But principal component analysis is deterministic, it's static, and here we have a stochastic version of that. Another thing which is interesting to see, one does not rely on just generating one curve, but one can take the number of curves in the scenario, in the training scenario, and use always 2 curves or 30 curves and move this window ahead and use this as a training data. And this would make you or put you in the condition to take the current observed curve as a sample, as a realized sample, and based on the sample conditionally compute the curve today or tomorrow. Or we can take the last 10 curves and simulate 20 curves in ahead. So that's quite a lot of possibilities to conduct the simulation. And as I have to point out again, it's that we have the Gaussian principal components. So we have the basic structures of the curves and can interpret them as the Gaussian components. Because we are running out of time already, I will just briefly outline the application to the volatility surfaces. In this setup, I hadn't had any information, so I created volatility surfaces by applying the SSVI model. And what I did here is I used 2 different SSVI models, generated implied volatility surfaces, and fitted a Gaussian mixture model to the joint dynamic or the joint distribution of both implied volatility surfaces generated from SSVI models with random parameters. And this is the outcome here, training data, and here's the Gaussian principal components for volatility surface 1 and volatility surface 2 here. But since I fitted it to the joint realization of the volatility surface, I am in a position to use, for example, these Gaussian principal components or the realized component here and condition on that to generate this one. And this is what I did here. This is the input for one of the curves here and the generated curves based that these values have been realized. And this is just a conditional simulation of an implied volatility surface. So quite interesting. Of course, any practitioner asks for arbitrage, static and dynamic arbitrage. And yeah, how could we handle arbitrage in this setup? On the one hand side is that you have to constrain the training. On the other hand side, you say the statistical learning method should implicitly learn this no arbitrage if the data is actually given and has no arbitrage in there. And I have tested both methods. So one is a suggestion for handling arbitrage by incorporating constraints here. And the other is by just assuming the data is what it is. And if it's arbitrage free, it should learn this arbitrage freeness. And if there is arbitrage, of course, the generated data may also have arbitrage. Yeah, so applied to yield curves, the one original versus synthetically made arbitrage free by not allowing negative forwards, but the training data had negative forwards actually. So I somehow altered implicitly the data. Maybe that's what you want, but maybe that's what you not want. So you can decide if you leave it in there or if you constrain it in the training and remove the arbitrage. But here are the differences for the different methods on yield curves. And again, differences for yield curves. Of course, if I synthetically constrain the curves to be arbitrage free, I would get different values if the underlying training data has arbitrage built in the curves. For the volatility surfaces, it worked very well. So the SSVI models were considered in this setup to be arbitrage free. I sampled 25,000 implied volatility values and checked the arbitrage afterwards. And it turned out that only a fraction of a percent is not arbitrage free. And yeah, that's quite amazing. So it really learned the arbitrage freeness of the input data. And here are some numerical results for that. And yeah, if you want to just have real arbitrage-free data or real arbitrage-free surfaces, you can apply an arbitrage repair afterwards. But this only has to be done in yeah, not even 1% of the samples actually. I'm not covering this dynamic arbitrage here. I just wanted to summarize actually that synthetic data generation can be as easy as with the stochastic sampling algorithm using only uniforms and Gaussians. That one can handle a lot of real market data in one or several dimensions. It gives a very good fit. It can be applied to backcasting, to synthetic yield curve generations, volatility surface generation, and by just using standard functionality from the scikit-learn package. These examples I showed, it's not more than really calling the fit function and using the stochastic simulation algorithm. It's not sophisticated, high parametric something like a neural network. It's just Gaussian and uniforms for the simulation. And actually, currently, I'm trying to extend the stuff using further results from Damiano Brigo, for example, where he had a possibility to set up a local volatility model in terms of a Gaussian mixture model somehow. And this gives a dynamic component, and one can there link a dynamic component on the risk neutral measure and the real world measure. And my hope is then using the results from the optimal transport from the Gaussian mixtures, you would have a connection of these two different diffusions and can generalize articles like the one from Harvey Stein, appeared several years ago in Risk Magazine, to move from Q to P measure. Okay, since we nearly reached the time, I think I stop here and taking some questions if some questions have appeared, or just sticking to some comments.
Absolutely. Yeah. Thank you so much, Jörg. This was an absolute pleasure to kind of, see the rigor and the math and also the work you already put together. There's one question about synthetic data generation in general. It may not be specific to the financial services industry. If there are privacy concerns and risk of memorization, how do we address it? And also, is there going to be overfitting? And how could you approach that to mitigate the possibility of memorization as a risk?
Yes, I think that's a problem. And I think this is also one initial starting point for these generative methods, so that people maybe for validation or for other stuff wanted to somehow give away somehow their data for validation, but they faced the problem of not being able to really give away the actual data. But what they could give away was probability distributions. So usually these probability distributions do not really have any information about a specific trade, specific weighting of assets and so on, but it could be, say, a portfolio value of certain trades. And if you have the probability distribution of that, you might be able to give it away as, say, a Gaussian mixture model. So just having the parameters which you give away, and you usually have no idea of how to reconstruct any positioning, any value of a specific trade. I think that could be interesting if you want to hand over some data to auditors, to I don't know, maybe regulators, and without really transferring trade data or other data which is relevant. I'm not aware actually of this memorization problem, and I haven't thought about that, what it has to be or has to do with overfitting at the moment. So I was just in this, just keeping the privacy by not giving away real data, but data that is embedded as a probability distribution.
Thank you. Thank you. There's another question. David Paulson asks, when backcasting, how do you take several steps to backcast short periods of time in sequence, or is it all at once? I know you mentioned about some conditional aspects. If it's the former, how do you determine the step size? And also, I would consider, just to add, I actually will embed my question. I was also thinking about when you're working with sparse data sets, wherein the continuity of time is not fixed step. How do you kind of factor that in when you do the backcasting?
Yeah, so the first question, I do several steps. So I'm not really, if I have maybe 1,000 time steps to backcast, I'm not doing 1,000 steps at one go, actually, because the idea by using a smaller step size and doing several steps is that I may miss certain trends in the data. Of course, if I do a very long term backcasting. But the number of step size, that's a delicate one. So usually with the interest rate models, I tried to have 100 steps actually. That turned out to be working quite well. But for equities, I observed that fewer time steps were necessary. And I believe, I haven't checked it yet, but I believe it depends on how volatile certain markets are. So in interest rate, often we have maybe some fluctuation, but not really big fluctuations, say. But in equities, it could be periods of real high fluctuation and then calmer periods, actually. And I think this has to do with choosing the step size. So in terms of really high movement in equities, you might miss certain things if you do a very large number of step sizes. And so you always have to find a kind of trade-off between the number of step size, so the length of the runtime of the algorithm, and incorporating this volatile behavior. I think it needs to be related to some volatility or some variation.
Absolutely. There's another question about how do you explain, actually, could you explain a little more about the control variate regression logic used in the backcasting example? As understood, the missing long-term rates were regressed against known rates for some overlapping period, and then the residuals from regression were used as a CV.
Yes, so actually, thank you that you mentioned that it is a great presentation. But to your question, actually, it's the control variate. The underlying idea was laid in the paper when I considered hedging. So I wanted to use, say, already given information to somehow stabilize everything. And option pricing and hedging, you could just use the underlying itself or some proxy underlying, which is moving like the asset you want to somehow calculate an option for. And it turned out that you could compute the delta in this setup. It's a stochastic delta, but it could be in the setting of Gaussian mixture models calculated analytically. So that is very interesting. And the same idea I applied here in the sense, as you mentioned already, that I used the 2-year, 5-year, 10-year, and 20-year rate as risk factors, and then construct a deterministic function, namely the regression, the linear regression or non-linear regression on the rates. I want to forecast and use the result as a already proxy, as a function of the underlying rates. But there's still some stochastic movement, and this stochastic movement is then modeled by the Gaussian mixture model. And this is the way you can incorporate this autoregression into the modeling and also have a little bit better fit than just using regression. It turned out if you do it for stocks, then the regression is not that accurate as in rates. But this has also again to do with a more volatile behavior or more idiosyncratic risks in certain stocks in that setup. And there the auto-regression you see is much more different for the regressed ones to the original series than regressed plus the Gaussian mixtures to the original. So the effect there is even more pronounced than I showed for the interest rates, actually.
Thank you. Thank you so much, Jörg. I wish we had another hour. I mean, I have so many more questions. I wish we could kind of, delve into all the last slides, which you were kind of, speeding up a bit, but I would love to kind of, continue the discussion offline. This is great work. Thank you for presenting this. I mean, it kind of builds up upon many of the things we were talking on a regular basis in the past, right? So, in the new world, we assume everything be model free, and we assume a really large neural network can capture all the idiosyncrasies of what we've seen in the data and potentially model in, which potentially also could lead to memorization problems because, when you have these neurons firing, when you don't have a formal model, the generalizability of the model becomes a challenge when you are focusing more on a metric, which may be accuracy or replicability of, past data sets. So I'm glad that you are able to bring back some of the core ideas of quantitative finance and making it available again. I'm also interested to kind of see. I know you mentioned about some of the generic things like fixed income and so, but with the new world being driven with every portfolio wanting to incorporate some amount of Bitcoin or some of these new products, how would this kind of fit in terms of being able to, I don't know if it could be a lot of different kinds of models put together, or even to factor in all these things which we have never seen before, and also event-driven aspects, which could potentially
definitely
cause these spikes. But again, it's a fascinating discussion. I would love to keep in touch and continue the discussion offline. For people who are listening online, we will make the presentation and the slides and also the link to the paper available tomorrow when the email goes out. And please stay tuned for future lectures. Next week, I'm going to be in California for Bank of America's retirement conference. I'm going to be giving a talk on Tuesday, actually on Wednesday next week. So we will not have a session next week, but when I come back, I'll see if I can redo the presentation for this audience on what I presented there. And we will continue the discussion. If you have any speaker ideas or any specific topics you want to discuss, please feel free to send us a note and we will try to incorporate that into our future discussions. Again, thank you so much, Jörg. Enjoy the evening, and all of you who are online, enjoy the rest of the day, and we will talk soon. Take care. See you.
Same from my side. Thank you for having me. Bye-bye, everybody. Thanks for listening.